Hello everyone, time for the 15.6 video. So let's go ahead and begin that. 15.6 is a fairly straightforward extension of what we've done so far in chapter 15. It's just we're still doing multiple integrals, but now we're integrating over 3 dimensions instead of 2 dimensions. So we're not going to spend too much time on the theory, because really the theory is all the same as it was for a function of two variables. Okay, so let's just kind of quickly run through it. So there is a little bit of a mental adjustment to make. All right, so remember that for a function of a single variable, for f from r to r, we could think of we thought of the integral as giving us the area underneath the curve, and that's fine. That's a kind of first impression to have, but we want to grow beyond that. We want to start thinking about it as just kind of a mathematical object, and then we have the two-dimensional. Let's see, for functions of from R2 to R, the integral represents the volume beneath the curve, or volume beneath the surface. Okay, so we're going from area to volume. So what happens if we want to do an integral over a 3-dimensional region? Well, first of all, well, I guess we could ask, okay, if a integral over 1 dimension gives us area, integral over 2 dimensions gives us volume, what are we gonna get from a integral over a 3-dimensional domain? It's not gonna be anything that makes real geometric sense, not anything we can kind of relate to the real world. And we can't even graph it very well, right? These graphs, okay, from 1 dimension to 1 dimension, R to R, I end up with a graph in R2, right? A 2-dimensional graph. When I have a function from R2 to R, my graph ends up being 3-dimensional. So if I was going to try and graph a function from R3 to R, I would end up with like a 4-dimensional graph, right? So that doesn't really make a lot of intuitive sense. There's no way to really draw it. So we can't really put these kind of nice, we can't really draw these nice graphs to kind of get a picture of what we can look at. We can draw the domains, right? We can draw the R3 part, okay? And that's mostly what we're going to focus on in this section. But the graphs themselves don't make a whole lot of sense. Now, we could kind of use the terminology from our previous sections as a kind of extend it to higher dimensions, right? So when I had a function from like R2 to R, the graph, which was something like this, right? That blue surface, we called that a surface. All right, and we could do the same thing for R3. We can call the graph of this, the curve that is produced by this, we could call it instead of calling it a surface, we could call it a hypersurface. So let's see, we called this a surface or a curve. We could still call this a curve, or we could call it a hypersurface. Hyper, you might see hyper pop up in our textbook or other textbooks, like hyperplanes, hypersurfaces, things like that, hypervolumes. Hyper just kind of means, okay, we're taking it to a higher dimension. Okay, so we could call this thing like a hypersurface or hypercurve. And we could think of the integral of this function as giving us, something like a hypervolume, like a 4-dimensional analog to volume. Okay, so it might not make a lot of sense by itself, but maybe if we kind of think of it as just kind of an extension of volume, okay, maybe it makes a little sense. But I wouldn't waste too much time, not that it's a waste, but I wouldn't devote too much time to kind of thinking about it like this. It's this way of thinking it's beneficial, but I would say it's only limited benefit. Okay, and maybe it's better to just start thinking of these integrals from R3 to R and R4 to R. Maybe just start thinking of them as like the mathematical objects they are. They're just the limit of Riemann sums, right? So we construct the three-dimensional integral just like we would the I suddenly got paranoid that I'm not recording. I am recording. Good. Okay, and I got my volume on. All right. So we construct our integral just like we would, or just like we did for functions of a single variable and functions of two variables. We kind of start with this Riemann sum, okay, where I have like a functional value, my f here at well, really, the better way to think about it is I'm integrating on a region, and I divide that up into a bunch of, in this case, boxes, three-dimensional boxes. And each of those three-dimensional boxes has some sort of measure. We can think about it as a volume in this case. And then I'm multiplying by like kind of a function value to kind of get this idea of the hypervolume of a box, right? And I've chopped my box up. I've chopped my graph up into a bunch of kind of four-dimensional rectangles or boxes, whatever you want to call them. And then I'm making the three-dimensional base of my four-dimensional rectangle smaller and smaller and smaller. And as I do, this sum is going to converge to our integral. Okay. Now, if that doesn't make any sense to you, just remember that, okay, we're starting with a sum that's giving us an approximation to the thing we're looking for. And then we're taking the limit as this piece goes to 0. And what do we get? Well, the three summation signs become our triple integral. My f at a finite number of points becomes my f, my function at all the points in my domain. And then this delta v becomes my dv. Okay. And just like we had for functions of two variables, we started out talking, we started out by talking about integrals like this, f, x, y, and then we said dA. And that's all well and good for theoretical purposes and notation. But then how did we actually calculate it? We took this thing and turned it into an iterated integral with actual bounds and whatnot. Okay, and then we use this to calculate our values. And we're going to do the same thing. So the line above here, this line is kind of our kind of theory, and how you'll often see it written in the general form. And how we're going to actually compute these triple integrals is we're just going to turn it into another. So the simplest case is, of course, when the region we're integrating on, R, or whatever it might be called for the particular problem, I often call it D. Okay, whatever this region is, that's what we're integrating on. The simplest case is going to be when that thing is just a box, just our three-dimensional rectangle. So x is just given by this condition. X is between A and B, y is between C and D, and z is between E and F. Okay, so now the region I'm integrating on in this simplest case is just a box, right? So I have my three-dimensional domain. This is just my domain. This is not the graph of my function, right? So maybe the region I'm integrating on is just a nice rectangle, or excuse me, a nice box. Could do it in blue. Okay, so that's going to be the simplest case. Okay, when I'm just integrating on a box. And that's similar to when we had functions from R2 to R. The simplest case was when we were just integrating on a rectangle, right? Okay, so in this higher dimension, F3 to R, excuse me, F FR3 to R. The simplest case is when we have just a three-dimensional box. Okay, and then we have our analog, or our Fubini theorem, right? We're allowed to turn this into an iterated integral by Fubini's theorem, and as long as everything's constant, all these bounds are constants, we can switch the bounds of integration freely, right? Okay. So an example, let's do a quick example. I'll just make one up off the top of my head. You know, there's nothing too much new here. Maybe we're given f, x, y, z is equal to, you know, whatever, call it just x times y times z. Okay. And we want to integrate on the region. You know, maybe you'll see it written like this in this kind of set notation. And then z is between, how about -1 to 0. Okay. So let's just integrate this function on this region. Okay. Well, I could start out by writing my, you know, triple integral. I could write my first line, I could turn it into my iterated integral. You don't have to do that, but it's a nice little notation. And so let's see, 0 to 1. Let's see if I'm doing, let's say I want to integrate in terms of z, y, x. Okay, that means this innermost integral is going to be in my terms of z. My middle integral is going to be in terms of y, and then my outer integral is going to be in terms of x. Okay, so I've turned it into my iterated integral. Okay, what does this become? Let's see, z squared over 2 from -1 to 0. Okay, and this equals z squared over 2 from -1 to 0. That equals what? Just 1/2, right? Let's see, is it 1/2 or -1/2? I plug in 0, it's -1/2, right? Okay. I'm gonna just go through this kind of quickly, so I might make some mistakes. Feel free to point them out to me. Okay. Next, I integrate in terms of y. So I get, let's see, I got -1/2 y squared over 2. And now I'm evaluating from 1 to 3. Okay, what do I get? I get 9 over 2 minus 1 over 2. That gives me 8 over 2, which is 4. Okay. All right. Simplify that. I pull out the constants. I get -2 integral of x from 1 to 0. X squared over 2, evaluated from 1 to 0 times -2 out front. And let's see, I get -2 times 1/2 equals -1. Final answer. So there's nothing too new. It's just integrating, you know, over integrating 3 times instead of 2 times. Okay. So in the simplest case, when we're integrating over just a box, very, very simple. Okay. All right. Now let's talk about integrating on general regions. Okay. So this is similar to 15.2 when we kind of increased the difficulty a little bit. Instead of integrating on just rectangular regions, we started having regions where you know, we had functions in our bounds of our integral. So we have the same concept here. And we move from the simple boxes to the more complicated regions. Now, in the previous in 15.2, what we allowed our double integrals, you know, it was fine to have one integral have functions. You know, maybe I had like g of x, like g2 of x, g1 of x, and then like a to b. Okay, so my y bounds were functions of x, and that's fine. And as long as that we do that on the inner integral, everything works out nicely. And then if I have constants here, I'm still going to end up with just a number as my output of my double integral. Okay, this will still just give me a nice numerical answer. Okay, and the same thing happens for the triple integrals, but for the triple integrals, we can have 2 out of the 3 integrals involve functions. So maybe we still want our outermost integral to have our constants for bounds. Like maybe we have, you know, whatever, a to b again. And then let's say that outermost integral is in terms of x. And then the two inner integrals can be functions of, let's see, I would, this one could be like a function of x. So this could be g1 of x to g2 of x. And then this innermost integral, let's say that's the dy integral, the y integral. This innermost integral could be function of x and y. Okay. So let's see what would happen. I have some region, and then my z coordinate is a function of x and y, right? So I integrate that, and all my z's in my function turn to x's and y's. And then I have, so now I'm at this stage, and now I just have a function of x and y, and I integrate it with respect to y and plug in my bounds, and all my y's turn into x's. Okay, and then I'll be just integrating here, and I'll have a function of just x. I integrate that, plug in my constants, and I get a number. Okay. So just like with the double integrals, the outer integral, if we're trying to find a numerical answer, our outer integral, we want to have the constants in the bound of integration. So let's, the next, you know, that's pretty much it for the section. I just have a couple examples here to show how this all works. And I can say something about applications at the end, but let's see how to apply these, how to integrate over these general regions. Okay, so this is a problem that was, I think, similar to something we saw in 15, maybe 15.2 or 15.3, maybe both. We're using a triple integral to find a volume. And that might kind of clash with what I said up here, right? Where we said like, okay, the integral of a R2, okay, when our bound is our domain is R2, or a region in R2, that's going to give us volume, right? Okay, and then we said, well, what's this thing? So now we're trying to integrate over a region of R3, but it's somehow giving us volume. But didn't I say it was hypervolume? Okay, so remember this trick that let's say I have a region R. Okay, if I integrate the function, which is just the number 1 over the region R, okay, this will give me the area of R, right? Similarly, if I integrate just the number 1 over my 3-dimensional region, this will give me the volume of R. Okay. And oftentimes we don't even write the 1, right? It's the same thing to just write dx dy or dx dy dz. Okay. So the only struggle here with these types of problems is figuring out what your bounds should be. Okay. Okay. All right. Okay. So an example, and we're gonna have to play with find bounds a little bit. Let's see, where were we? Did that one? Yeah, we're done here. Let's find volume of the region R, which is bounded by the coordinate planes and the plane 2x plus y plus z equals 4. Well, first of all, let's recall what are the coordinate planes. The coordinate planes are just like x equals 0, y equals 0, z equals 0. Okay, so those are my coordinate planes, and then we're also bounded by this plane here. And I want to find the volume of that region. So I know my integral that I'm trying to set up, okay, I could write it like this: r of the number 1, okay, dx dy dz. Okay, so I just need to figure out, there's nothing complicated about what's going inside this integral. The only thing I need to do is find the bounds. Okay, so how do we find our bounds? It's similar to 15.2 and 15.3. My first suggestion is to get a picture of in your mind of what these bounds look like, or excuse me, this region looks like. Okay, so I've drawn my region here. Really, it's mostly determined by this plane here. Okay, so I draw this plane in green, and then the coordinate planes just are chopping me off at these axes, right? Okay, so that my region is just that kind of, what would that be, a tetrahedron, something like that. Okay, so that's that green, and we can kind of outline our entire region. So this, the interior of this thing is our region. Okay. I want to find the volume of that. So I need to set up my integral. Okay, I need to figure out my bounds. All right, how do you do this? Okay, maybe this was hard for you guys in 2 dimensions, and now we're doing it in 3 dimensions. Okay, so here's the strategy. You're going to pick one direction to be your constants. Okay, and in this example, we have a couple choices, and one is probably no better than the others. Maybe in some examples, it's really obvious which direction should be your constants. Okay. In this example, let's pick our z to be our constants, meaning in my integral up here, okay, when I do my dz bounds, I want those to be my constants. Okay, so what are my bounds for my z variable? Remember, this is the z-axis, x-axis, y-axis. Okay, so what are my bounds for z? Well, z seems to start at 0 and stop here, so 0 to 4, right? Okay, so that's step 1. Pick one direction to be your constants, figure those out. Okay. Step 2, let's just take a cross sections, anywhere along our curve, excuse me, along our region, and let's consider that cross section. So I'm going to take this yellow cross section of my region here, and I'm going to lay it flat out on the page, so to speak. This yellow triangle is just it's 2-dimensional, right? And really, it's in terms of x and y, right? Like if I'm basically going to lay it flat on the page, and then it's just like in a kind of XY plane. Okay. So I'm gonna lay that cross section down flat on the page. And now what I'm gonna do, step 3, is to I'm gonna make bounds for this 2-dimensional region using our techniques from 15.2. Okay. Okay. So it's kind of similar to what we just did. I'm going to pick one direction to be my constants, right? So I'm trying to write the bounds, like forget about the three-dimensional stuff. Okay, if I wanted to integrate over this region, do a double integral over that region, how do we do that? Okay, so again, I'm going to pick one direction to be my bounds, actually my constants. Okay, so in this, we're going to treat, this triangle does depend on the z value. Okay, maybe this is at, call it z sub 0. Okay, so that triangle does depend on z sub 0, but we're going to just think of it as constant right now. Okay. So what? Now let's write our y's. Let's pretend our y's. Actually, let's try and write our y's as constants. So where does my y start and end? Okay, my y begins at 0 and it goes to whatever this point here is. Well, what is that point? Okay. It's going to depend on what this line is, right? Well, this line is coming from this plane, right? Okay. So let's pretend our z is constant, okay? And then this line is given by, the equation of our plane, right? So we're pretending our z is constant, so we'll write z sub 0 instead of z. Okay, so what is the equation of that line? Well, it's this. Now I just want to write that in a way that helps me, okay? What is this? We're still trying to figure out what this value here is, right? Well, this value is going to be when x is equal to 0. Okay, so to figure out what that value is, I just plug 0 in for x in my equation, and I get y plus z0 equals 4. In other words, y equals 4 minus z0. There. Okay. Okay. So that's what that value is. Okay. And z0 is fine, but when we plug it into our integral, we do just z's. Okay. All right. So I've treated I've found my z bounds. I'm treating my z bounds as constants, and then I'm picking cross sections, and I'm pretending the z is constant. Okay. And now I also want to pretend the y is constant in these bounds. Or excuse me, not pretend, but I want to kind of treat those as my constants. Okay, and I get this integral, these bounds for this integral. Okay, last step, I need to find my bounds for x. Okay, and now I need some function here, right? What are my bounds for x? If I was just integrating this 2D region, okay, I'm treating this z like a constant, so these are constants. And then I need to integrate, for x, I need to integrate one of my bounds, at least needs to be a function. Okay, so what is that function? Well, it's this line here, right? My x is, all my x values are between this line, this vertical line, which is y equals 0, or excuse me, x equals 0 to whatever this line is. What is that line? Well, we have some equations for it, right? And of particular interest are these two, and really this one, right? We don't want our x to go beyond this line, so we want our x's to be like less than or equal to that line. So what does that tell me for my bounds of integration? My bounds for my x integral should be 0 to the equation of this line, which I've rearranged into this. Okay, and those are my bounds. And then the next step is just to integrate. Okay, so let's see. I integrate with these bounds, and then the rest is just normal integration. So I'm integrating the number 1 essentially. Okay, so first I'm integrating in terms of x, and what do I get? Oh, I'll get negative y over 2 plus 4 minus z over 2. Okay. And now I'm integrating all that in terms of y. Okay. Which brings me here. All right. And I plug in my bounds once I've found that integral. Okay. And it actually simplifies pretty nicely into this integral from 0 to 4 of 4 minus z squared over 4. I'm just going to expand all that in the numerator and divide out the 4. And it becomes a very easy integral of z. And all that works out to 16 over 3. That's my volume of that region. Okay. Obviously went through this integration stuff pretty quickly. Hard part is setting up the bounds. So see if you can follow what I'm saying to this step and then just integrate on your own and see if you get the same numerical result. All right. For the last example of this section, I want to do a problem that's kind of difficult, but I think it's doable for you guys, and it'll be good because it's going to show us, it's going to be a good kind of introduction for the next section. Okay, so let's look at this problem. We want to find let me make sure my screen sharing's on and I'm recording. Okay. Yes, okay, all set. So let's find the volume enclosed by the surfaces y equals x squared plus z squared. This is a z, and y equals 8 minus x squared minus z squared. Okay. As a preface, remember, okay, we were talking in the beginning of this video how integral in one dimension gives us area under a curve. Integral of a two-dimensional domain gives us volume beneath a curve. And then we said, okay, triple integral is kind of this hypervolume. But now I'm saying use a triple integral to find volume. Well, how can we do that? Well, if this, and really it's kind of more about these two. If the function we're integrating is just like the number 1, it'll give us the volume beneath the curve. But what is the curve? The graph of this would be what? If I'm integrating on this region, I'm just integrating the function 1. I'm just integrating, whatever the region is. If the region's like this, it's the region, and then with just a height of 1. So it's just like a cylinder, right? So the volume of this cylinder is the height, which is 1 times the area of the base. So this volume will be the same as the area of the base, okay? So integrating the number 1 on our region gives us in 2 dimensions the area, and then in 3 dimensions volume. Yeah. Okay. All right, so that's the rationale of why we're using a triple integral here. Okay, so to reiterate, we want to find the volume of this region. We can do that by doing the triple integral on our region of the number 1. And, it's the number 1. We don't even have to write it. We can just write it like this, dx, dy, dz. So the hard part is finding the bounds, the correct bounds for my region. Okay, so I want to find the bounds for this region, and we're going to do this in Cartesian coordinates, and then in the next section, we're going to see maybe a slightly easier approach. So we're working with this idea that we can write, maybe one of my bounds as constants, and then the other 2 as functions. Okay, so that's going to be what we're doing here. So what should be my constant bounds? If I've drawn these curves,
if you graph these curves to kind of get a picture of what your region looks like, you end up with this picture below. Okay, y equals x squared plus z squared is this blue curve that actually kind of continues widening like this, right? And then y equals 8 minus x squared minus z squared is this green curve. And then the area enclosed by them both is kind of this oblong, this kind of like football shape, right? So this is our region. And as I said, if you graph this, the constants that are clear are this 0. It's our curve starts at y equals 0, and it goes until y equals 8. Okay, so maybe that should be my constants that I'm using, my actual constants, 0 to 8. Okay, and then maybe that should be my last integral that I do, integrating in terms of y, since those are the constants. Okay, but we can actually make this a little bit easier, okay, by looking at this curve and saying, well, this thing's going to be, this blue region that I just erased should be half the volume, right? Because this thing's kind of symmetric around this line here. So really, and then this should be right in the middle, right? This should be at y equals 4. So really what I can do is I can integrate from 0 to 4 and then multiply by 2. And that'll save us some problems in the long run. So let's do it like that. Okay. So I got my constants, 0 to 4. And then I'm just integrating this blue region. Okay. So I can kind of forget about this green stuff for now. Okay, that'll probably be as much as I can erase simply. Okay, so I'm integrating this blue region really, then I'm multiplying by 2. All right, so how do I integrate this blue region? Well, I got my constants, 0 to 4. And now I'm gonna, there's gonna be some functions involved in my other bounds. To figure out what those are, what I'm gonna do is I'm gonna take a cross section like this yellow circle, and I'm gonna lay it flat on my page. So what does my cross section look like? It's a circle. I'll draw a very poor circle here. Okay, so this is my white shaded region here, laid flat on the page. So this would be the x-axis. This would be the z-axis. Now let's say this circle is at a particular y value. Call it y0. Okay, so we get a circle. What's the outer edge of this circle? Well, the outer edge of this circle is the outer edge of my surface, right? And this is given by the equation y equals, it's this equation here, y equals x squared plus z squared. Now, if I'm looking at the particular y value, call it, y0, I have this equation. Okay. All right, so this is coming from the curve y0 equals x squared plus z squared. So what is the radius of the circle? This is the equation of a circle, right? With radius square root of y0. Okay, so the radius of that circle is square root of y sub 0. And in particular, okay, right here, we have a width of y sub 0, radius of y sub 0, and then this point would be negative y sub 0. Okay, and those could be my x bounds. Okay, and that was for a particular choice of y sub 0, but that's true for all our y values. So no matter what circle I draw at what y value, okay, we have these bounds. So I'm just going to write square root of negative square root of y to square root of y. Okay, it's my x bounds. And then what are my z bounds? Okay, it's kind of like section 15. 2 material where, like, okay, I've picked my constants to be, I'm pretending these y0s are constants, and then what are my functions going to be, my function bounds? Well, one of them would be this top curve here, right? Which is, I need to write in terms of z. So in terms of z, this is if I have y0 equals, or just y. If I have y0 equals x squared plus z squared, then y minus x squared equals z squared, and square root of y minus x squared equals z. Okay, so this top curve is like the positive square root of y minus x squared. And then this curve down here that I left white is negative y minus x squared. Okay, so those should be my z bounds. Okay, and then the rest is just integrating. Let's see, and integrating in terms of z first, then x. The rest is just integrating. And it's not an easy integral. Okay, so figuring out bounds in this one's a little bit difficult, and then integrating is kind of difficult. So I'm doing a difficult one, and again, you'll hopefully see why the next section is so useful once we get to it. I'm going to do this the same exact problem in the next section using a different method, and we'll see it's significantly easier. Okay, so integrating in terms of z first, well, you know, there's no z's, I just have the number 1 there. So I integrate in terms of z. And what do I get? I get 2 times y minus x squared. Okay, you can integrate this on your own to see why that's true. Fairly easy first step. All right, and let's go ahead and bring this 2 outside with this other 2 to become 4. Remember, this 2 is coming from the fact that we're just finding the area of this blue region and then multiplying by 2 to get the volume of the blue region, multiplying by 2 to get the volume of our total region. Okay, so those 2 2's combine to give us the number 4 outside. Now I'm integrating this square root of y minus x squared. Well, if you think back to Calc 2, that's a trig sub integral. So I do x equals square root y sine theta. And then dx equals square root of y cosine theta d theta. I make my substitution in the inner integral. I pull the y out through the square root and becomes square root of y and 1 minus sine squared theta. Then I have another square root of y cosine theta d theta. Okay, combine these 2 square roots of y into just y. 1 minus sine squared, well, that's cosine squared, right? Square root of cosine squared is cosine. Then I have 2 cosines. I'm back to cosine squared. Okay, so this is a y cosine squared theta d theta. Integrating cosine squared is hard, so I use that double angle identity. 1/2 1 plus cosine 2 theta. Okay, bring the 1/2 outside. With the 4, it becomes 2. Okay, now I can integrate this. And what? This is still integrating in terms of theta, right? I'm missing an integral sign there. All right, integrating in terms of theta, I get y theta plus sine 2 theta over 2 d theta, or excuse me, dy. I would evaluate this at bounds. Well, remember I made a substitution, so I want to undo my substitution and use my original bounds. Okay, so how do I undo this substitution? Remember what the substitution was. It was x equals square root of y sine theta. So x over square root of y equals sine theta. And remember how we undo these trig substitutions. Okay, sine theta is what? Opposite over hypotenuse. So I can draw a triangle and think of the opposite as x. hypotenuse as square root of y. And then this side would be what? Y minus x squared, just by Pythagorean theorem. Okay. All right, so I got a triangle. All right. And then I have the fact that, well, if x equals y sine theta, then what? X over square root of y equals sine theta. And so sine inverse of x over square root of y equals theta. So let's look at this and let's look at our triangle. That should be enough information to undo the substitution here. Well, I have a theta, right? I have a theta. And I just said theta is equal to sine inverse of x over y, square root of y. Okay. And then I have sine plus sine 2 theta over 2. Sine 2 theta is hard. This is all in terms of 1 theta. Okay, so what's sine 2 theta? We'll use the identity sine 2 theta is 2 sine theta cosine theta. These 2's cancel, and I just have this sine theta cosine theta. Now I can figure out what sine theta and cosine theta are for my triangle. Sine theta would be opposite of our hypotenuse, so this over this. Cosine theta is this over this. Now I have everything in terms of x and y again. I can use my original bounds. Okay. Now, when I plug in my bounds, okay, I'm plugging this in for x, positive square root of y. I get sine inverse square root of y over square root of y, which is 1. Okay, and then when I plug it into this portion, I get, let's see, in the square root here, I get square root of y minus y, which is 0. Okay, so this term gets canceled out when I plug in square root of y. Okay, so I just have sine inverse of 1. Okay, and then I subtract, I plug in, let's see, negative square root of y. Okay, so sine inverse negative square root of y over square root of y, which is negative 1. And then let's see, this term again goes to 0. Okay, so I have this. Well, what's sine inverse of 1? That's pi over 2. What's sine inverse negative 1? That's negative pi over 2. So I have 2 integral from 0 to 4 y times pi dy. Pi is a constant. You can pull it out front. 2 pi 0 to 4 integral of y dy. Integrating y squared over 2 from 0 to 4 times 2 pi. That's 2 pi times 8, 16 pi. Final answer. So a lot of work, right? It was, a fair amount of work just finding the bounds, but then it was very difficult to integrate. Not impossible, but difficult. So this one's difficult in Cartesian coordinates. We're going to see it's simpler in the next section.